Hello everyone, my name is Huanzhou. I'm from Imperial College London. Today I'm presenting MSRL, a distributed reinforcement learning system using the Dataflow Fragments. In past few years, reinforcement learning achieved some remarkable results. It started with AlphaGo. Right? After AlphaGo beaten the world champion Go game several times, people start using our algorithm in many different fields, such as controlling the data center, to control the automatic driving cars, or to help designing a chip, or in the future it will be used to control nuclear reactors. So let's have a look of first look at the classical RL algorithms. A typical RL algorithm contains three components: an agent, a learner, and an environment. In a training loop, the agent first uses the neural network in the learner to do the inference. And then the learner sends the inference result, also known as the action, to the environment. So the environment can use those actions to do the simulation. And the agent will collect those simulation results from the environment and send those results as the training data back to the learner. The learner can train and update its neural network. This is a straightforward process. However, to develop an efficient RL training system, there are several challenges. The first challenge is that the neural network in the learner may use some very large model. And the second challenge is that a good reinforcement learning system needs to accelerate the entire training loop, not just the neural network training and inference. The third challenge is that the system needs to handle the diversity of the algorithms. So next, let's have a look at those challenges in detail. So we first have a look at large model size. From this figure, we can see that in past 3 or 4 years, the RL algorithms are developed with billions of parameters, and some of them even have trillions of parameters. That means the training of those models can be really time-consuming and expensive, which requires some really fast hardware. However, this is what the problem comes from, where the problem comes from. We don't have very fast hardware. This is because due to the Moore's law, the performance of CPU and GPU can only be doubled in every 18 months. But at the same period, in the same every 18 months, the model size can increase by 35 times. That means that the latest hardware is not efficient enough to process the latest model. And this gap here can only be filled or overcome by using distribution. The next problem we're looking at is hardware acceleration. To look at this problem, let's start with some RL system, existing RL system. Let's start with a function-based system, such as ZRL, Acme, and RL Graph. Those systems exploit the entire training loop using Python functions. The advantage is that the algorithm is very easy to develop using these systems. However, due to the limitation of the Python, only a small amount of the code can be parallelized or accelerated by the hardware. Right? Naturally, and because most Python code can only be executed with CPUs. Therefore, the performance of this system are very limited. To overcome such problem, people developed actor-based systems, such as RIA and RLE. In this system, they express the entire training loop using actors. The advantage is that those actors are very flexible. They can be deployed or parallelized by many different types of hardware. And they can, however, the actor is a fairly low programming model. Therefore, developing algorithm using this system is not an easy task. And third type of system here is a data flow-based system. In those systems, they tend to use data flow operators directly to implement the RL algorithms. That means the algorithm implemented in this system can be executed very efficiently, since those operators can be mapped to to different hardware accelerators and be parallelized and can be executed very efficiently by those hardwares. However, this approach is developing algorithms using those operators is a very challenging task. And by looking at these three different types of systems, we can see there is a trade-off between the usability and the performance and the hardware performance, let's say. Therefore, we would like to develop a system that balances the usability and also has some very good hardware acceleration support. The next challenge here is that the system needs to handle the diversity of RL algorithms. This is because RL algorithms tend to have very different communication or computation patterns. We provide three examples here. The first one is PPO. Right? In this algorithm, it contains multiple agents and a single learner. And the agents and the learner are communicated through some synchronized group communication output. On the other hand, the A3C algorithm, which also contains multiple agents and the learner. But this algorithm communicates agent and the learner through asynchronous send and receive operators, that is point-to-point communication. Therefore, this algorithm has very different communication requirements from the PPO. And in the end, let's have a look at mu0. In mu0's algorithm, there contains multiple agents, and also it contains multiple learners. And this multiple agent and the learner are connected through a centralized replay buffer. So the structure, we can see the structure of this algorithm is very different from the first two. In addition to that, the mu0 algorithm also uses Monte Carlo tree search in agent to perform the inference. This provides another opportunity for parallelization, right? Because Monte Carlo tree search can also be parallelized inside of the agent. That's also another challenge which system need to handle. Therefore, hence, we need the diversity of those algorithms suggests that we need to have a system that's flexible enough or strong enough to support all different kinds of communication and computation patterns. So to answer all those challenges, we developed mandatory reinforcement, or MSRL. The key idea of MSRL is that we decouple the algorithm specification from the algorithm execution. To achieve that, we use three key technologies in MSRL. The first one is that we define the computation as a data flow graph. In MSRL, we call it fragmented data flow graphs. Secondly, those data flow graphs can be accelerated on heterogeneous devices. That means that each fragment within the fragmented data flow graph can be assigned to CPU or a CPU. And in the end, MSRL also supports flexible ways to distribute your algorithms. We achieved that by using distribution policy, which can support many different types of parallelization and distribution scenarios. So let's first have a look at how to use MSRL to develop algorithms. In this example here, we developed a PPO using MSRL. So MSRL provides two kinds of APIs. The first is we call it algorithmic classes, which is some base class that the user need to inherit to develop their own algorithm algorithmic component. For example, these PPO actors inherit the actor class provided by MSRL. And in addition, MSRL also provides some API code, such as environment simulation or replay buffer insertion and sampling. By developing your algorithm with all those API, with all the MSRL API, we can translate the algorithm from the Python code into some data flow representation. And those data flow representation is called fragmented data flow graph. So a fragmented data flow graph is a heterogeneous data flow model. That means it uses different or independent data flow representation. But it can use different algorithmic component of the RL training loop. So for example here, fragment A represents the action computation implemented using some data parallel operators from the DL engine. And the fragment B represents the environment simulation implemented using Python function. And fragment C implements a learner or model training using CUDA kernel. And those fragments can be executed on different devices. So for example, the fragment A can be executed on GPUs, and fragment B we will assign to CPUs since it's Python function. And again, we will assign the fragment C to the GPU since it's implemented using CUDA. And to support or to parallelize the fragment execution, we can have multiple copies of each different fragment. For example, here, we duplicated fragment A 3 times, and we assign each copy to a different GPU. So those copies can be executed in parallel on different devices. And all those fragments is connected through some communication operation, such as broadcast or gather, or you can use send operator as well. And this will form a complete training loop. So the next question here is, how do we generate those fragments? Well, in MSRL, it generates a fragment based on the information provided by the distribution policy. So there are two key information provided by the distribution policy that will be used in fragment generation. The first one is the boundary information between the fragment, and the second one is the instance of fragment. Well, the boundary of the fragment, the MSRL use the boundary information to split the original algorithm into different fragments. For example, here, with boundary informations, it splits this algorithm into 3 different fragments, and each fragment contains some kind of original code. And then the MSRL use the instance of fragments to generate a executable fragment. So those fragment instance is actually some Python class that has placeholder in it. Those placeholders represent class name or member functions or etc. etc. So the MSRL can copy those code into the correct place into those fragment instance and replace the placeholder there. Therefore, it can generate an executable Python class, which guarantees the correctness of the algorithm execution. So the next question here is, how do you select the distribution policy? Well, there is no definite answer for that, because you need to select distribution policy based on many different criteria. But here we can provide some guidelines through some examples. The first one is, let's have a look at first example here, right? It's called a single learner with cross-grain synchronization. In this distribution policy, the worker 4 contains the learner, and it uses that learner to do model training. In addition to that, this policy also collocates the actor and the neural network for actor to do the inference with the environment simulation on the same workers. That means this system can have very good performance in data collection because it collocates the inference and the environment simulation on the same worker. However, this system, it will communicate after each training steps. This distribution policy or the learner needs to send the updated neural network parameters to all other workers. So if you have a very large model here in the learner, this communication can quickly become your bottleneck of this policy. Well, that means this policy is best suited for training with small models. On the other hand, we have a DPB or single learner with fine-grained synchronization policy. In this policy, the worker 4 again contains a learner, but this time the worker 4 will use the learner for both inference and the training. That means the worker 1, 2, and 3, the actor collocated with worker 1 to 3 will not perform any inference on the neural network. Therefore, in this distribution policy, it needs to exchange the training data at every environment simulation step. This is a very frequent communication pattern, right? Because in general, each algorithm needs to perform thousands of environment simulations. However, if you only have very few GPUs, this policy can be very good in that scenario. These two policies give us some hint, right? For example, there is a trade-off between the neural network cost and the network bandwidth cost, right? We need to pick up the policy to balance those two costs. However, this selection, we should let the user to switch between the different policies, because the user will have very different hardware environment, and those hardware environment will have very huge impact on different distribution policies. Next, let's have a look at MSRL system architecture. Well, first, it contains a coordinator. This coordinator contains a fragment generator. The fragment generator uses the user-provided algorithms and distribution policy and some algorithm configurations to generate the fragment. And then the the coordinator uses the fragment dispatcher to dispatch the generated fragments to different workers. Each worker will contain some execution backend, for example, a Python runtime or a DL training engine. And at the top of each worker, there is a fragment optimizer. The purpose of those optimizers is that when the fragment dispatcher dispatches multiple instances of same fragments to a same worker, the optimizer can fuse or group those fragment instances into one big instance to avoid the overhead of processing those instances sequentially. And then all the workers can communicate through some communication operators provided by the DL engine. Since those operators generally have very good performance, it guarantees the communication will not become the bottleneck very quickly. So next, let's have a look at some experiment results. First, we compare the MSRL with GRE. In this experiment, we use a 4-node cluster, and each node in the cluster contains 8 NVIDIA V100 GPUs. And in this experiment, we use PPO and A3C algorithm. So both are in this experiment, both MSRL and Ray are used in the same parameter setting and same distribution policies. So it's it's a fair comparison to make sure it's a fair comparison. So as we can see from this result, MSRL outperforms Ray in both algorithms. So for PPO, it outperforms Ray about 3 times. And for A3C, it is about 2 times faster than Ray. The reason of this is that the MSRL is able to accelerate the entire training loop instead of just part of it. Unfortunately, Ray here, it didn't accelerate the entire training loop. And another advantage of MSRL is that it used some customized communication operators provided by the underlying DL engine. Therefore, it's be able to pick up the fastest communication channel instead of just use some default ones. So next, we study the scalability of MSRL. In this experiment, we use a 16-node cloud cluster, and each node in this cluster has 4 NVIDIA P100 GPUs. The algorithm we use here is the Maple algorithm. In this experiment, we compare MSRL with its sequential baseline. So for MSRL, we increase the number of when we assign each agent to a GPU. And so by increasing the number of agents, we also increase the number of GPU used in MSRL. We can see from the result that as the number of agents increase, the execution time also increased in both systems. This is because the larger the agent, the large amount of agents will generate large amount of training data. Therefore, it requires longer time to process. However, the growth of MSRL is much slower than sequential version. For example, here with 32 agents or 32 GPUs, due to this massive distributed training, the MSRL is 58 times faster than sequential version. And this suggests that MSRL can efficiently process distributed RL training algorithms on large-scale hardware. We also looked at the throughput here, right? Since as we mentioned, increasing the number of agents will increase the amount of training data, and hence it will also have significant impact on the throughput. And the result is that with 64 agents, the throughput here is almost 7,600 times higher than the 2-agent time. That means the MSRL is able to process very large amount of data in reasonable time. So that concludes our presentation. So to conclude, so in this presentation, we demonstrate that the distributed reinforcement learning is now becoming a major workload in today's data center systems. Cannot support such workload very efficiently. Therefore, we need a new abstraction to efficiently distribute and execute those RL algorithms. Therefore, we proposed the fragmented data flow graph, which is a new abstraction that is able to accelerate the complete RL training loop by mapping the different algorithm component to the heterogeneous hardware. It also support the flexible distribution policy to match the different hardware resources scenario in different data centers. And that's everything. Thank you. Oh, and the code of MSRL is available on GitHub. And thank you. If you have any questions, please ask.